controllers will come in. It'll be fine. Okay, so welcome again. Thank you all for coming. Misha and I are going to split this lecture today. So I'm going to go first, and I'm going to answer the following question that will hopefully give some further motivation for what we've been yapping about the last two lectures. So I started off by saying, you'd like to know that a constant negative curvature closed manifold even exists, okay? And I sort of discussed the construction of that last day, my last day. And so I'd like to add some more to that. I'd like to sort of up the ante and show you that this construction that I've been claiming that you should learn and love over this week is actually useful. And so I'm going to add to this with Betty numbers that are all positive for 1 less than or equal to k less than or equal to n minus 1. Okay? I bet you can do 0 and n, right? Somehow it's going to be the middle ones. Okay? And so it's precisely this construction, and it's a very beautiful idea using symmetry that allows you to achieve this. And so this is my goal for the first half of today, at least. And so this is what's called the Milson-Raghunathan method. All right, so there's an original paper, a very famous paper due to Milson, that does this for B1. And there's a follow-up paper by Milson and Raghunathan that is equally beautiful, if somewhat typo-ridden, and does the general case. And so that's what I'm going to discuss now. And I'm going to do this in an example. And the point is that I'm going to point out each step you need, and you can make this robust to work for this entire arithmetic construction. Okay? You just need to find the right involutions that fix the right quadratic forms and blah, 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 blah. But let's just keep one example in mind and see how we can start to build some homology classes in that example. And each step will just involve some simple linear algebra symmetries that you can try to take along for the ride. So we had this quadratic form Q, which was minus alpha x naught squared plus the sum of xi squareds, where alpha squared is 2. Okay? And using the two choices of a square root of 2, we saw that this Q became minus root 2 x naught squared plus 1 to n xi squared, and then the second one we get plus okay, from our two choices of a square root of 2. And so the point was, on the first step, this was isometric to the standard minus x naught squared plus some xi squared over the real numbers. Right? So there's a real change of isometric here. I just mean there's a real change of basis. Well, I should say similar. So plus scaling vectors. Okay. So this gives us a model. So we get a hyperboloid from this, and the hyperboloid is a model of hyperbolic space. And in this case, so you note that this star does not represent 0 with real entries. Okay. And so what that tells us is that there does not exist a V in k to the m plus 1, non-zero, so that when we pair it into this form, we get 0. Okay? So if we take this group G, okay, the automorphisms of this form, changes of bases that preserve the form. And we're going to let's just do it this way. The things that have integer entries I don't think I said it yet. It's our field. Is there anything I want to say before I do this? No. Then we can embed G of K. Right. So since this is equivalent in the sense that I said things are equivalent in the first lecture, to the standard form that you build the standard hyperboloid model of hyperbolic space with, you get an embedding of this group into O(n)(1). And in this case, this is a positive definite form, so you get the standard orthogonal group. And we project this, call this pi. And I'm going to define gamma to be SO and 1 intersect pi of the integral stuff. Okay? And so the point here is that this is orientation preserving isometries. And this little O is telling us that we preserve the upper hyperboloid. Okay, so this acts on Hn naturally. If you take the full SON1, you could also maybe swap the two, and you have to worry about that. But okay, it's also the connected component to the identity if you care. Okay, so if we take our hyperboloid to be the set of V R plus 1 such that minus 1, and we have gamma acting on H discretely by orientation preserving isometries. And we saw last time we can pass to a subgroup. And assume the action is free. Okay. And so this thing, I didn't say this last time. I should have, and I didn't. The Godemont compactness criterion so it's sort of unclear. So he claims in his paper that this is known for these groups, but there's not a proof in the paper. So it's a little murky whether he actually proved this or not. But anyways, there's certainly a complete proof in this paper of Borel and Harishchandra. This quotient is a compact manifold. We assume it's acting freely, so this is a compact manifold. Okay. And again, all that's happening here, you're taking the linear transformations with root 2 entries that are preserving this quadratic form, and they act on this hyperboloid, and they give you a compact manifold. Okay. But the key, just to again be clear, is it's already like I can't use star because I already did, but the whole point was for this. So this fact that it doesn't represent 0, so this is the way that you make sure it's compact. Okay, so just for the purposes of this, we have this algebraic way to make sure that we get a compact manifold instead of something that's, say, non-compact finite volume. Great. Okay. Good. Wow, that's great. That's our goal. It's going to be construct finite covers to M. This is the gamma H. With positive first Betti number. Okay, we're going to do this via involutions in this group that we defined. And in fact, I'm going to add normalizing this gamma. Okay? So the point is we're going to be able to go back to the linear algebra here to just do linear algebra over this number field to find lots of symmetries of the quadratic form, and we're going to use those symmetries of the quadratic form. Just think about reflections, right? If you're a geometric group theorist and you love yourself a reflection, this is what's happening. Okay? That's going to give you the b n minus 1. Is going to be reflections through vectors, okay? And so this is going to give us embedded submanifolds, actually. They'll in fact be totally geodesic because they'll be fixed points of symmetries with non-zero homology classes. Okay. HK of M and non-torsion classes. Okay. All right, so let's make this super explicit so that you can, on your walk back down the hill today, you can just start constructing these. So our model.
Do you mean embedded in hat?
Sorry, I didn't hear.
Do you mean like embedded in M hat or?
Oh, it'll be M hat. Yeah. Yeah. Thank you. So we have this model. It's written down somewhere. No. Where did I put it? No. Oh, yeah, there it is. So we have this hyperboloid model. So we have H as above. And we have a base point. What base point I'm going to take? I'm going to take this one. You have 4 through to 2. Okay. So I think you can maybe check that has norm minus 1 for the quadratic form I picked. And so remember, the tangent space to y naught of H is a set of vectors that pair to 0 with our y naught. Transpose. But our form was diagonal. Remember, it was just minus square root 2 x naught squared plus x1 squared plus xn squared. Right? So what vectors are perpendicular to this? Well, this is just the span of E1 up to En, right? Oops. And the thing to note here is that if we restrict Q to this space, to this tangent space, we get the standard dot product. Okay, so if you know a little bit of Riemannian geometry, I'm just telling you that these are actually normal coordinates at the point. Right. So as you change the point, as you start moving this vector around, the restriction will change, and it's because it's not flat. But okay, so you're really getting, this is all set up and designed, so you're getting standard normal coordinates for the Riemannian metric at this point. And now let's pick a splitting. This tangent space, which I'm going to call V, is W1 plus W2, where the dimension of Wi is going to be Ki with K1 plus K2 equals n. So we get a full splitting. All right. And we want to do this. So, well, maybe I'll say one remark that's just true about hyperbolic space being homogeneous. That's the first thing to remark. So there's an isometric embedding. Of hyperbolic Ki space into our hyperboloid model through Y naught with tangent space. At Y naught equal to Wi. Right. And the point is, you're just going to restrict your form to the right subspace, and you'll be fine. Okay? So there's just a sort of restriction, and you'll get some quadratic form in a smaller number of variables. That quadratic form will give you a model of hyperbolic space, and you'll get a natural embedding of that hyperboloid model. It's an isometric embedding. Okay? So do some notation. So I'll let G be so N1. K is going to be the stabilizer in G of Y naught. So this is isomorphic to SON, right? Because it's the isometries. In this case, it's clear to see that the things that fix Y naught have to stabilize this form. That's the standard form. And so it's naturally isomorphic to SON. Okay? And that's how you see the homogeneity, right? So SON acts transitively on planes of different types, and so you can you see the homogeneity. Orbit stabilizer. Now you have to be careful. This is topological orbit stabilizer. It's not just as sets. This is actually more robust. Right? So G acts transitively on the hyperboloid with point stabilizer K. So we actually get, this is actually a diffeomorphism, but you can worry about that yourself. And the remark I want to make, because this will come up later, reason for introducing all of this, is that gamma mod G is a K bundle over gamma mod G mod K, which is gamma mod our hyperboloid. So we see that gamma mod G is compact. And more generally, it's if and only if. We've already assumed it's compact, but right, there's an if and only if statement. This quotient of hyperbolic space is compact if and only if this is, because it's a bundle with compact fiber. All right? But anyway, so there's going to be a point where I'm going to actually care about this being compact instead. So for example, we'll take W1 to come from the span E1 up to EK, and W2 to be the rest. And we get involutions. Sigma I, they actually live in this group stabilizing the point. with plus 1 eigenspace each wi, okay? And so in the example case, what are we looking at? We're looking at one, a k by k identity, and then a minus n minus k identity. You just take this block matrix, and this will be sigma 1, and then 1 minus ik, and then I n minus k, that's sigma 2, okay? So these both preserve my quadratic form. They both fix my base point, and they fix the appropriate subspace of the tangent space. All right? And moreover, we can make sure, this is in general, sigma 1 and sigma 2 commute, and their product, sigma 1, sigma 2, is the involution of all geodesics through y naught, okay? Now the point is that this is going to come from what's called the Cartan involution. We're not going to need those technicalities at the level we're talking today. There's something called a Cartan involution, and this product gives you, by conjugation, the Cartan involution. Okay? But here you can sort of plainly see what's going on here. Okay, these definitely commute because they're block diagonal matrices. And the product is minus the identity. So what is that telling me? That's telling me at y0, the action of the product is by minus identity. What is that doing? That's flipping all lines passing through that point. So that's reversing the direction of all geodesics. Okay? So we won't get into too much of the mechanics of why we want that assumption. But somehow, certainly at the level of linear algebra, given a pair of subspaces, you can find a basis so that it's in the example coordinates, and then it works. Okay, but let's just say we step out, we go into the jungle, and we find these two involutions that commute and whose product is minus the identity at our chosen base point. So we're going to define GI to be the set of G and G that commute. That's an I. So you can say this is ZG sigma I. Now remember, this is an involution, so I can drop inverses. So I'm going to save IMPA a little money by using a little less chalk. But remember, these are involutions, so that's conjugation. So what you can see is this is isomorphic to S of O K I 1 cross O N minus Ki, otherwise known as Ki plus 1 plus 1. Okay, so this here is acting on Hi, which is the image of this lower dimensional hyperbolic space, okay, this other hyperboloid. And then this right here is acting on the normal bundle. All right. I'm going to define GI bar to be the subgroup preserving orientation. Right, so the point is that our G, we're taking the orientation preserving isometries of Hn. But now I can act on this totally geodesic subspace and its normal bundle. And so I could act by orientation reversing isometries here, and orientation reversing isometry here, and then the product will still be orientation preserving. Okay? So this is actually SO ki comma 1 cross SO n minus ki. Is this a plus or a minus? Or it's just, oh no, it's just, there's no plus 1. It's just that. Yeah, sorry. Adding is the hardest part. Maybe this is less important, but I'll notice that G1 intersect G2. This is, again, you need determinant 1, but it's O K1 cross OK2, so these are the orthogonal transformations at the point that preserve our decomposition of the space. Okay? But this is actually maximal compact of each GI. Okay? Again, we're not going to use this in any significant way. It's a little fun fact to think through, that, if you so choose. All right. So far, I've said nothing about the group, right? So what's going to be the key hypothesis? So we're going to have to work a little harder, because we're actually going to prove a theorem. We're not just going to do linear algebra, but it's pretty close. There's actually one point where there's some pain and suffering, and we're just not going to do it. But the key hypothesis is that each of these commuting involutions normalizes gamma. Okay? And so the point is, we're going to use the arithmetic to pick so that okay? So somehow we're going to do the linear algebra carefully. Now, for the form I picked and for the WIs I picked, it works, right? Because what's the point? Our big gamma had, what was it? It was the matrices with entries in square root 2z. Do these have entries in square root 2z? Oh my goodness, they do. Okay. Okay. So in a specific example, this is actually very easy to arrange. You'd like to know that for every choice of quadratic form and blah, 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 you can always do this, and you can. All right? Yes?
Perhaps you should briefly explain geometrically what you're doing now.
I am. That's the point. I'm good.
You are constructing cycle,
I'm getting there. I'm getting there. I'm getting there. Yes, I am. That is absolutely, that's the most true thing that's been said during this entire lecture. Right, so what's going on here? So one, these sigma i's are now isometries, induce isometries. Of our M. Okay. And the fixed sets of these will give our submanifolds. All right. That's going to be the point. And so what do we want to do? We've set up some algebraic things. Okay, this is just elementary algebraic topology. I have something that normalizes a group. I get an action of z mod 2 for each I on my manifold. So I induce an isometry by, say, Mostow rigidity or something. Okay, so that part's not so bad. But what we want to do is actually prove that the fixed sets of these give us closed, embedded, totally geodesic submanifolds. That, with a little bit more suffering, represent non-zero homology classes. Okay? And the point is that what we're going to get to start is that locally, you'll have some, say, y1 and y2, and they're going to intersect in a single nice point. Okay? Now you can look at the cat product on homology. Now if these just intersected like this is what you see in the universal cover. We have a copy of hyperbolic k space, a complementary hyperbolic n minus k space. Okay? And they intersect in this one point. So this is the image of y0 in the quotient. But we've taken a quotient by a group action. These could have self-intersections. These could meet each other in other points. There's some worry. Locally, we've arranged something so that if we take the cat product in homology, we get a non-zero class in H0. Therefore, these both have to have non-zero classes in HK and Hn minus k, right? But what if there was some other intersection that had a minus orientation intersection? Then they would sum out to 0 and the argument would be wrong. So we have some work to do, okay? I've got 10 minutes to do that work, but it's some beautiful math, so I think we're going to be okay, okay? But yeah, so let's get into this precisely. So there's one step of the argument that I'll give an almost complete proof, modulo some stuff that all of you smart young folks can handle. And then the second part, there's a little bit of pain and suffering, but I'll say a few words about it at least. Right, so I set gamma I to be the set of gamma and gamma that commute. Gamma. So this, by definition, lives in GI, which acts on HI, right? And this is tangent to tangent space WI. Okay? Now, what if this group was trivial? What if this was trivial, then I'm not going to get a compact manifold, okay? So you have to be careful here. But by definition, this is in GI. And I'm going to set yi to be gamma I mod is hi, okay? Or this is isometric to hki, all right? And so our first goal is that this yi is an embedded, I'm going to say it in the order I'm going to prove it. Compact embedded submanifold. This is of RM. All right. So it's going to be proposition 1 and 2, and you can guess by what's underlined what they're going to be. So yi is compact. All right. And so up to some fuss with covers of Lie groups. All right, so there's going to be there's a little annoying bookkeeping about what group you're in, but I think you know, it's Thursday. We just can't. We just can't. I can't, which means you definitely can't. That's not an insult to you. It's just you're sick of me already. Okay, so up to covers of Lie groups, the key is the following result of Selberg due to Selberg. I think the proof I'm about to give is actually due to Mostow. So if we have lambda in G with lambda mod G compact, this is a discrete compact, and tau is an element of lambda, infinite order, maybe I'll say. No, I think it's still fine. Yeah, it's still fine. Yeah. Then you take the centralizer, intersect your lambda, and that lives inside the centralizer. You take this quotient. This is compact. Okay. By the way, if you love yourself a reflection group, which I'm going to cry if you don't, when you have a reflection group acting on Hn, this is what tells you when you pass to finite sheet of manifold covers of that reflection orbifold, the face groups become totally geodesic submanifolds. Okay, this is the same step. All right, so this is a beautiful proof, so I'm just going to do it. So you take the map. Map C from G to G, that C of G is G tau G inverse. Okay? So you map G to the conjugate of tau under G. All right, so C of lambda lives inside of lambda because groups. And C is continuous. All right. So what this implies is that C inverse of C of lambda is the set of G and G. So that C of G is in C of lambda is closed. All right. And we're going to do a calculation. Sort of G gamma G in, tau. And yeah, it's all taus, okay. If you have this conjugacy, then we see that delta inverse G lives in the centralizer of tau. So that means that G, which is delta inverse G, deep fact here, lives in gamma ZG of tau. So this is actually equal. So C inverse C gamma is actually this set of products. Okay? So then this is closed. All right. And the last step is an exercise, which is that ZG of tau intersect gamma mod ZG of tau can be identified. This is a homeomorphic to gamma mod gamma ZG of tau living inside gamma mod G. And so now you have a closed subspace of a compact space. So it's compact. A beautiful argument. Okay? And that tells us, so now, I'm bringing it home. Oh, don't worry. We're going to get our break. So now what do? We take lambda to be the group generated by sigma 1. May as well throw in sigma 2. And gamma, this is a finite extension of gamma. Right? I've just added these two order 2 commuting elements. But each yi is zg of sigma I intersect gamma, intersect lambda, let's say. No, it is actually gamma. All right, so check this too. But so we see that the yi's, which at this point we only know we're immersed in M, are compact. Okay. I'm on my last page, which actually this only this is what we want to do. Okay, so far we know we have an immersed compact submanifold. The key is we actually wanted it to be embedded. So proposition 2 is going to give the embedding. This is due to Jaffe. And this is that yi. It's actually an embedded submanifold. Okay, so what would be the point? So we're just going to do I equals 1. For some strange reason in Mills and Raghunathan, they do the case I equals 2. But I'm going to do I equals 1. So what would happen? So we have this hi. If we had a self-intersection, then there exists a gamma in gamma that's not in our gamma I. So here we're taking I equals 1. So that gamma h1 intersect h1 is non-trivial, right? We'll have some deck transformation that causes the self-intersection downstairs. All right, so we're going to prove this doesn't happen. All right, this is a beautiful argument. So suppose you have x1 prime in h1, gamma and gamma with x1, gamma x1 is x1 prime. Right. Then consider the element, I don't even need my notes. This I can actually do. So consider the commutator of this gamma with our reflection sigma 1. Oops. Well, maybe I'll do it the other. See, now I did need to look. I want in the other order. If you don't do it in the right order, it doesn't work. Let's see. This is in gamma because sigma 1 normalizes gamma. All right. But now I'll let you do this in the privacy of the Hotel Vermont or over a coffee. But point is now you check. Let's give this a name. Let's call this delta. You check that delta x1 prime is x1 prime. Okay? And it just sort of follows out of the definition. Things just sort of fall down because you know that sigma 1 acts trivially. Right? Sigma 1 acts trivially on H1. But gamma acts freely. On the whole hyperbolic plane. So this delta equals the identity. All right? Then this implies that our gamma is inside of gamma 1, right? Because gamma now commutes. With sigma 1, and gamma 1 was by definition the centralizer of sigma 1, okay? But that means that it's just a deck transformation. For y1, so we get an embedding. Okay. So now I'll just say, so we can take a break. I among all of us am ready for a glass of water and a break. But so there's a fuss with double cosets. To ensure that y1 intersect y2 is all points with positive orientation. Okay? So if you want to know about, I want to get to our break, but if you want to know, I can show you the setup of the double coset problem. It's not hard. The solution is not easy. It's not completely trivial, but in a given example, you can do it by hand. Okay? You can find, and this is by passing to a subgroup. Okay, so you have to pass to a cover of M, but you can make sure that you always have positively oriented. So if you lift y1 and y2 to M hat, you get that their cat product is non-zero and h0 of M, so you get non-zero in H. Ki of M mod torsion. Okay? So again, if you want to see what the double coset problem is and the kind of challenge you have to go through, it's much more complicated, but I think let's have a break. Okay?
Welcome back. This will be the last half an hour of our mini course. Tomorrow we will have a shorter day because it's Friday after a long week. So by various reasons, it's natural to talk a bit more about commensurators, commensurability, and relation of this algebraic object with totally geodesic subspaces and geometric cycles which appeared in our lectures. Well, let's recall the definition of commensurator. So we have a subgroup of a Lie group. Well, gamma is going to be a lattice for us. So subgroup gamma in G. And we define commensurator of gamma in G as well, the set of all elements who, when we conjugate by this element the subgroup gamma and intersect with gamma, this has finite index in the conjugate and gamma itself. well, it's purely algebraic definition, and the question is what it has to do with our main topic. So to understand a little more, let's look at an example. So example, illustrative example is take SLN Z. Well, you can take SL2 Z or SLN Z, doesn't matter for this purpose. So it's as we know, it's an arithmetic subgroup of SLNR. And well, the basic claim is that this commutator of gamma will contain all matrices with determinant 1 and rational entries. So it's actually very easy to prove this claim. Well, I guess there are many ways, but what do we want to do? So we take some matrix with rational entries, and we want to conjugate by this matrix our matrices with integer entries, and see that there is some finite index intersection, right? So one of the ways to look at it would be as follows. Okay, let's take, say, L1, the least common multiple of denominators of the entries of A. So these are rational numbers. They have numerators and denominators. And finitely many of them. We take least common multiple of these numbers. And we also will need the same for A inverse, because we conjugate by now, well, how to find this finite index subgroup, which is in the intersection, so something here. Well, one of the ways to do it, which I think is the simplest possible, is let's look at the congruence subgroup. Corresponding to the product of this L1, L2. So this will be given by, so what are the elements of these congruence subgroups? These are matrices which are equal to 1 identity modulo the product L1, L2. So they all have this form, identity versus this product multiplied by some matrix. So we require that it sits in SLNZ. And here, this M is some integral matrix. Right? And well, so easy fact is that this is a finite index subgroup of gamma. Finite index subgroup. Now, if you act by conjugation by A on the elements of this congruence subgroup, what you see that, okay, there are some denominators, but they cancel by this product of the denominators, and as a result, this conjugation is going to be a subgroup of the group of integral matrices. And by the construction, it's finite index subgroup. So this is something which will sit in, so say this gamma 1. It's not necessarily equal to gamma, but it doesn't matter. What it matters is that it's contained in both gamma and gamma conjugate, and the index is 5. Well, so for any rational matrix, we can see that the intersection will be finite using elementary arithmetics. What are the conclusions of this? Well, the first conclusion is that, you know, rational numbers are dense in real numbers.
Why does finite start with conjugate root?
Well, I hidden a little bit here, but what I said is true. Okay. You ask why it's finite index, right?
It's good about it is finite index separate from gamma, but matters that why does finite index in the opposite?
Well, it's this is contained in gamma. You conjugate.
It seems to me that you want to.
So I want to gamma A conjugate this conjugate of gamma. Yeah.
It seems better if you write gamma of L1, L2 is contained in the conjugation of A, SLN Z, A inverse.
No, but it's also contained in SLNZ because all the matrices here, as I showed you, have integral entries, and they all have determinant 1. So yes, it contains in conjugate of SLNZ, and it's contained in SLNZ. It's contained in intersection, and that's why the groups are. That's why A belongs to commensurator. Okay, we can maybe discuss later, but this is more or less the argument. So now the more interesting part is what it means. So notice that, okay, SLNQ is dense, is a dense subset in SLN R. Well, perhaps this requires some thinking, but I don't need to convince you that rational numbers are dense in real numbers. And this is the same on the level of vectors and matrices. So it follows from definition of real numbers in some way. Well, another observation, actually remark, a side comment. It is not necessary true that, and I think it's usually false, but okay, let's say that it's not necessarily true that commensurator equals to So what I want to say that commensurator is actually bigger than SLNQ, and we had examples of matrices, for instance, of Jorgensen involution, or of the last example I gave in the first lecture, where the matrix with some quadratic irrationals and as entries was still acting by rational transformations and sitting in commensurator. But there is no contradiction here because, okay, commensurator can be bigger. But for density, this is already sufficient.
You mean in this case that it depends on n? So in some dimensions is equal, in some dimensions is not equal?
I think in all dimensions it's not equal. No? I don't remember either. But, well, in dimension 2, what happens? Let me not think about it now.
Well, yeah, there's GLs. So you take a projective you take something in GL and you take a square root of it.
So, okay, let's make it more precise. Thanks to the question of Pliny. in fact, commutator strictly contains SLN. I think it's correct. Well, now we can talk about general case. So gamma is arithmetic. Subgroup in G implies always that commutator of gamma is dense. This is due to Borel. Well, roughly speaking, the same idea works, but you need to do it over number fields with all these admissibility conditions and take care of some details, but it's not a difficult theorem. It's okay, one of the basic results in the field. The difficult theorem, and quite surprising, well, perhaps not much less obvious fact, is that also converse is true. So, and this is due to Margulis. So Margulis proved superrigidity theorem of Margulis and used that superrigidity theorem to show that if commutator is dense, it's actually possible from this dense subgroup, step by step, recognize arithmetic structure that, well, rational and integral structure which defines an arithmetic group gamma. So density of commutator implies arithmeticity due to a fundamental result of Margulis. But this also often stated in a slightly different form. So let's give another statement. Margulis dichotomy. Well, there are two possibilities. Either gamma is arithmetic, lattice, and that's if and only if commutator of gamma is dense in the corresponding Lie group. Or the second possibility is gamma is non-arithmetic, if and only if commutator of gamma is a lattice. Okay, in G is a lattice in G. So in this case, it will be the maximal lattice of G, the unique maximal lattice, which contains given. Yeah, and gamma will be of finite index in this commutator. You'll get all these corollaries like at once. Also, uniqueness of maximal lattice you get from here in non-arithmetic case, because if there will be two maximal lattices, then okay, then you arrive to contradiction quickly. Well, so this is about arithmeticity and commensurability. One may ask how it relates with our stuff of totally geodesic subspaces and etc. The thing is that, well, perhaps also before talking about that, I should mention that it is known that non-arithmetic lattices in real hyperbolic spaces do exist. Okay, in dimension 2, it can be proved by looking at the space of lattices and deformations. In dimension 3, there is also argument related to dense surgery. procedure. In higher dimensions, there are known constructions. They were mentioned several times during the talk. So we know that this case actually is possible in real hyperbolic spaces, and in complex hyperbolic spaces, this is a big open problem if there exists any non-arithmetic lattice in complex dimension bigger than 3, okay, at least 4. Well, now what it tells us about totally geodesic subspaces, in particular, let's look at this class which I defined, so FC subspaces, and for them we can state the following dichotomy. Using what we know about construction of FC subspaces and Margulis arithmeticity dichotomy, we can state that for FC, say, dichotomy, we have the following. So this is in our paper. Well, there are two possibilities. Either gamma is arithmetic. Let me see how I state it. Now we are looking at not only at the group, but geometric objects. So let M be a hyperbolic n-dimensional finite volume orbifold. Can be it can be manifold or orbifold, it can be compact or non-compact, all is allowed. There are two possible cases. M is arithmetic, if and only if it has infinitely many FC subspaces. And the second part, M is non-arithmetic. If and only if it has at most constant versus, so this constant depends on the dimension, versus volume of M linear function bounds the number of FC subspaces. Well, perhaps the easiest part to explain now would be why arithmetic M has infinitely many FC subspaces. We already know that for each type of arithmetic M, we can construct at least one FC subspace. We know for type 1 from the first talk, from type 2 from, okay, at least from what I tried to convince you in the second talk, and for type 3 from Leonie's talk in the first week. So for each, we can give example of one FC subspace. And then we know that commingurator is dense. So you take any element of commingurator, conjugate your, say, involution, and you get different FC subspace, and you can get countably many of them by conjugating by elements of commingurator. So this you get like for free, infinitely many, if you only get one. This trick doesn't work for non-arithmetic ones because commingurator is discrete. And it's possible to make it a little bit more precise, so to actually bound the number of to bound the number of total geodesic subspaces in terms of the volume of this manifold, and observe that the bound is linear in terms of volume. So there is some more work to do here. I don't think 5 minutes will be enough, but it's not a difficult argument. We use first of all, Margulis arithmeticity theorem, and secondly, there is a previous work of Ari Levitt, I think, on conjugative classes of finite subgroups of lattices. So you can bound the number of conjugacy classes of finite subgroups of a given lattice by covolume of lattice that he did, and that gives you bound on the number of possible involutions or finite subgroups in commensurator of gamma in non-arithmetic case. And that translates to the bound on the number of FC subspaces. Now, final result that I would like to mention is a more general theorem by Bader, Fisher, Miller, and Stover. That was proved before. Okay, I don't put the dates, but this was earlier. So what they were able to prove that in non-arithmetic case, the total number of totally geodesic subspaces is finite. So there is another dichotomy which comes out, which says that either there are infinitely many totally geodesic subspaces, okay, FC non-FC, or there are finitely many of totally geodesic subspaces. You don't need any FC.
Dimension 2 or more, right? So all dimensions.
No, yeah, of course. M is, if M is non-arithmetic, then it has finitely many totally geodesic subspaces of dimension at least 2. Maximal. Okay. I knew that I will miss some. Thank you, Matthew. Maximal totally geodesic subspaces mention greater or equal than 2. And of course, well, the proof is different. You cannot deduce it from Margulis theorem, and what they did is they proved another rigidity theorem. And from that, we're able to deduce this result. Also, we don't know, the proof doesn't give you any bound on this number. So
But could it be 0? Could it be that they are many?
it could be,
We don't know a single example in dimension 4 and greater with no totally geodesic codimension 1.
With no.
Yeah, every known non-arithmetic hyperbolic 4 manifold has a totally geodesic hypersurface.
because they're constructed from arithmetic one
Sorry,
gluing.
what does maximal mean?
Maximal means not contained in, properly contained in other totally geodesic subspace. Otherwise, you can.
Because you have arithmetic totally geodesic subspace.
Yeah, you can have so you basically in all known examples in higher dimensions, you do have arithmetic totally geodesic subspace of codimension 1, and that one in turn will have infinitely many totally geodesic subspaces, but that infinitely many are not going to be maximal. They all sit in one arithmetic bit. So that's basically the reason to put maximal here.
And Philippe Lowry and Wells' result is the same, but for negative curvature, right?
Yes.
Yeah.
They
And the proof of that result, okay, half of the proof is this theorem, and then there is another, no, not theorem, method. So that,
Completely different. Fleet dynamics.
it's not completely different. Well, okay, we can discuss it later. So the other question, and let me just go, how to say, preview your other possible question. If there are examples of non-arithmetic ones with totally geodesic subspaces which are not of this FC type, and yeah, there are. For instance, Gromov-Petetsky-Shapiro gluing locus will be non-FC. However, that, okay. We know some examples, and we know very little about this number finitely. And here we have reasonably good control of the number. All right, I think I will stop here. It's time for the picture.